Happy Thursday, everyone. Actually, it's Maundy Thursday. Okay, so this is uh, Maundy Thursday of the Passion Week, and the Passover meal would have been had today. Thought it was really cool. I think it was last year in chapel when Dr. Chasnov and um, I think it was Michael Schur, they did the Seder dinner up on the stage. That was an interesting insight into the whole Passover meal and the meaning behind some of the things. I hope that this weekend, despite all of the hectic nature of what's going on, that you have plenty of time to reflect on our salvation, on the way in which Christ fulfilled so much of what is celebrated during the Passover week. In fact, he fulfilled it all. And I pray that you're able to spend good time with family, even if it's a smaller group than usual. You're able to really focus on what matters, namely our glorifying God, Lord, the salvation that we enjoy in His name. And you're able to encourage one another to that end. Want to thank everyone for coming out on Tuesday. I thought that was fun. It was kind of departure from normalcy, and it's always a good thing to kind of connect back together in that way, especially given these times. We might try something like that maybe in the last couple of weeks as well. In general, I do just want to leave class time open for question and answers, just so that you are sure to kind of have that time reserved to get your questions answered. But we did cover a lot in that meeting. If you haven't gotten a chance to check that video out, or if you missed it, I'd go check it out. I didn't post anything about the first couple of things. Those were easier examples that you'll have time to explore things like that in your homework. The first two we did were basically maybe these three, or actually we might have done all three of these ones, in fact. But then we got into these harder problems, namely, what's going on with the Platonic solids? Okay, Platonic solids, and this is Platonic not in the sense of, relationships, but Platonic in the sense of Plato, the great philosopher. Okay, he actually ascribed spiritual meaning to these solids. He thought it was fascinating that there was only a finite number of them, and that you could think carefully about how to even prove that there were only a finite number of them. Okay, this is interesting history for these solids. What qualifies a solid as being Platonic in nature, or one emanating from the mind of Plato, if you will? Well, you start with regular polygons, okay? And you build a solid from them, and you kind of want to think of the polygon as being filled in, so that there's skin in there, and then you build the solids from those. So of course, the smallest regular polygon is the equilateral triangle. And when I try to build a solid from that, I'm going to have at least 3 triangles coming together at a point to make that happen. And when you do that, it turns out you get this. Okay, so hang on a sec here while I try to expand this window out. Give me just a second. So the smallest number of triangles that can come together at a point are 3 equilateral triangles, and that's what a tetrahedron is. Okay, turns out that if you do that and you keep going around and keep squeezing together 3 equilateral triangles at a point, you'll end up with a 4-sided solid called the tetrahedron. Okay, and that's what we have right here. Okay, and then it turns out that if you, okay, so what's the next number of triangles that could come together at a point. And by the way, the Platonic solid has to have the same number of things coming together at every point so that you have this nice symmetry going on, okay? The next number of triangles that come together at a point are something called an octahedron, okay? I don't have one of those, but basically that means you have 4 triangles coming together at a point, 4 triangles coming together at a point, equilateral triangles. And we will kind of look at the cycle index polynomial in that particular case, but I don't unfortunately have one of those. But what I do have is the next one up, which is an icosahedron. That's this, okay? So what if I take equilateral triangles and I put them together 5 at a point like this, okay? So 5 at every single point. Okay, well, it turns out you're going to get this shape right here. And how many triangles does this even consist of? You know, it's incredible. Well, it turns out, look, if you see on the top, so on the top right here, you have 5 triangles coming together at a point. And then if I call this the bottom, it looks exactly the same. Okay, so you have these 2 kind of north and south poles of this is the icosahedron. Where you have 5 triangles around a vertex and 5 triangles around a vertex up at the North Pole and the South Pole. And then what about around the belt of this thing? You kind of have this belt of triangles going around like this. Well, you have 4 downward pointing or actually 5 downward pointing triangles and 5 upward pointing triangles, and they alternate. Okay, so there's a total of 10 going around the belt. Okay. 10 triangles going around the belt of this thing. Okay, and that's interesting. So, so that means you have 10 around the middle, you have 10 upstairs and 10 downstairs. That's a total of 20 triangles. How many vertices do you have? Well, you have 5, 6 upstairs, and then, you know, 5, 1, 2, 3, 4, 5, 6 downstairs as well, okay? So you have total of 12 vertices on this thing, okay? 12 vertices. 20 triangles, 12 vertices. And I'll let you think about like the number of edges, but this is the so-called icosahedron, okay? And then what? So we have the tetrahedron, we have the octahedron, we have the icosahedron. If I tried to put any more triangles around a point, you know, I'd be in trouble because I would no longer have any depth to this thing. If I tried to squeeze in another triangle, since all of these are 60-degree angles, if I try to squeeze in one more, I would end up with 360 degrees, and that would just be flat, okay? So there are no more, and this was the thing that Plato thought was so interesting. There are no more of these. Just flattens out, and I can't build any more of these special solids from equilateral triangles. So then he said, well, what about squares? Well, look, I need to be able to take at least three squares together at a point to give me a solid, and that's where the cube comes from. And then guess what happens if I try to stick 4 together at a point? Well, it's flat again. So that's it. This is the only thing that you can build a Platonic solid. This is the only thing that you can build with squares to get a Platonic solid. At every point, you have 3 squares coming together. Okay, this thing, of course, has 8 vertices, 6 faces, and the number of edges here is 4, 8, 12. Okay, so 12 edges on this particular thing. It's a pretty cool little puzzle here as well. Okay, so one thing I want to do today is actually go a little bit deeper with a couple of these examples, extract the cycle index polynomials of ones that we haven't already done, argue that the symmetries are completely accounted for. There aren't any other symmetries, okay, that we haven't missed any, okay? Because when we did that little in-class activity together where we were going through and doing the cycle index polynomial for the tetrahedron and for the cube, we just kind of said, oh, look, yeah, here's some symmetries, but how do we know there aren't other ones, right? Well, we're going to be able to argue why that happens to be the case, why it is that there aren't any other ones at all. We're completely done, okay? So we're going to argue what the symmetry groups are for these things, you know, to let these things float around in three-dimensional space. We're going to come up with the cycle index polynomial, and in some cases just re-verify that the cycle index polynomials are what they are. And then argue that there aren't any other symmetries at all. And then next, that'll set us up beautifully for next week. Next week, we're going to be dealing with Paulia's enumeration formula. That will really be the last topic. And the book's presentation is a little bit, I don't know, it's not super clear, okay, what's going on. So hopefully I can put together something that's maybe a little bit clearer and articulates with a little more crispness what's going on. And we'll get some amazing things there. The great depth of understanding that we'll have with the cycle index polynomial will inform how to do what we want to do there. And there, what we're going to do is we're going to build a generating function from the cycle index polynomial that doesn't just deliver the number of colorings. It will do that also, but it will also deliver the number of colorings that have a particular pattern inventory. So like if I say, okay, how many of these have like 2 black vertices, 3 red, and 2 green? Then the Pauli enumeration formula, the generating function that we'll get from that will actually deliver that to us for free. And it's something that will arise directly out of the cycle index polynomial. All right, so let's get to it here. Here we are staring at the tetrahedron situation. Let's look at the tetrahedron one first, which is this little shape right here, yeah, okay. And the other day we argued what the symmetries actually are, okay, just so that I remind you. Let me kind of expand this out and we'll talk about this together. One of the symmetries was we put an axis through each one of the vertices and we spun, and that axis went down through the opposite face down here. Okay, and we kind of spun it like this, okay? 1, 2, 3, right? But actually, there was only 2 rotations because the third one is really just the identity, okay? Okay, so for each vertex, we had one of these rotations, and it was rotation by 120 degrees, because 120, 240, 360, we're back to the beginning, yes? So that gave rise to how many of those types of things? So this is rotation at a vertex. We were doing 120 degree rotation, 240 degree rotation. The cycle structures were the same for those, because basically it just spun the bottom vertices into each other, right? So you had a cycle of length 3, and of course the top vertex, the one that you're spinning around, is fixed, yeah? So that thing is in its own cycle by itself. So you have a 1 cycle and a 3 cycle. That's why you have the x1, x3. How many of these do you have? Well, you have 120 degree and 240 degree rotation at each vertex. So there are 8 of those, which is where this 8 came from. And then the identity, right? So that's this x1 to the 4th thing. So there you had a bunch of, you know, the identity is just a bunch of 1 cycles, and there are 4 of them. Since we have 4 vertices, we're just having this thing operate on the vertices in this particular case. Okay, and what was the other operation that we were doing? Right here it says axis midpoint of opposite edges. Well, it looks like this. Remember, what we did is we kind of took one edge and then its opposite edge, and we put an axis of rotation through the middle of those, and you rotate by 180 degrees, whoop, like that. Whoop, yeah, 180 degrees. You're back to the 180 degrees, and then you're back to where you started. 180 degrees, then you're back to where you started. There it is. Okay, and how many of those are there? Well, there's, well, how many edges are there for this? There are 6 edges, you know what I'm saying? And each pair of opposite edges, okay, each pair of opposite edges gives rise to one of these. So there's 6 divided by 2 equals 3 of these special rotations. Okay, right, 3 of those special rotations. And why in the world? So if you kind of, stare at this for a minute. 3x2 squared. Okay, so there are 3 of them, x2 squared. So apparently there's two cycles. Why is that? Why is that true? Well, the top vertices, those 2 guys right here are kind of cycling into each other. And the bottom 2 vertices that are kind of front back, those are spinning into each other. Do you see that? So that's why you have 2 cycles of length 2. So hence the x2 squared. And then there's this 12 right here, yeah? It says 12. So there's a total of 12 things. We had the 8 rotations at a vertex, the identity, and these 3 guys right here. It's a total of 12. And the fact that we have a 1/12 right here is trying to point out the fact that there aren't any more of these things. All right, this is a complete group of right. First of all, Burnside's theorem doesn't require that we have every single symmetry. We just have to have a group of symmetries. Clearly, all of these things together is going to give us a group, but we'd like to know whether there are other ways to float this thing into itself. Well, how could we argue that there aren't any other ways to float this thing into itself? So here I'm going to write on here a little bit. Okay. Let me write on here. Here we go. Okay, so why aren't there more? Okay, so this 12. Okay, why not? Why not more? Okay, why not more? Well, think about this. So think about a vertex and an edge taken together. Okay, so I don't know, this top vertex right here and like this edge coming out towards you in the little screen right there. Okay, a vertex and an edge. Okay, how many destinations are there for a vertex? So destinations, destinations for a vertex. Okay, how many possible destinations are there for a vertex? Well, there's 4 total vertices, so there are 4 total places that it could go. And then we think of the fixed edge, so destination for a fixed edge on that vertex. Okay, how many places are there that an edge could go? Well, think about it. I mean, it's just got to spin to another edge on that vertex. So, there's only 3 places that it could go. It can't like detach itself from that vertex. So 3 places that it could go. So 4 destinations for our vertex. 4 destinations for our vertex. Okay, 4 destinations for our vertex. And 3 destinations for an edge attached to that vertex. Okay, so this thing right here is equal to 4 times 3, right? 4 is the number of vertex destinations, number of vertex choices, and 3 is the number of edge choices at a vertex. Okay, so there's 12 possible places that a vertex and a given edge could go, but we've come up with 12 total symmetries. Okay, so that there can't be any more than 12. That's it. There has to be exactly 12 because we found 12 and there are only 4 times 3 possible destinations for a vertex and an attached edge. Okay, so that's it. That's all there are. Okay, now let's talk about the cube for a minute. Okay, so that sort of re-justifies where this cycle index polynomial came from for the tetrahedron. And we know what to do with this thing. We know how to get the number of colorings from this. Just plug in all of the variables equal to the number of colors. and you'll get the total number of colorings with that many colors. And you might say to yourself, why in the world do we have these x1, x3, x2 things? Why not just have it be x, right? Well, it turns out that that sub-indexing is going to be very important when we go to prove Pauli as a enumeration formula. It's setting us up for something that's coming down the road. So we want to preserve that structure, preserve the fact that this x3 corresponds to a 3 cycle, and this x1 corresponds to a 1 cycle, and this x2 corresponds to a 2 cycle, okay? That structure will be important later on. All right, and then last time we actually finished with the cube. So let's talk about the cube a little bit here. Let's expand the picture of the camera here so that I can look at this. So remember here, so first of all, so let's think about this. At every vertex, okay, every vertex I have 3 edges attached, okay? So if I concentrate on a vertex and an edge, just like I did in the case of the tetrahedron, just like we did in the case of the polynomial earlier, if I concentrate on a vertex and an edge, how many possible destinations are there for that vertex and edge? Okay, so let's just kind of, I'm going to go in here and annotate down here so that you can see this. So the number of destinations for a vertex edge partnership. Okay, by partnership, I mean that the edge emanates from that vertex, is equal to, so think about this. I want to make sure that we're not missing any symmetries. Okay, a vertex edge partnership is equal to, well, how many vertex destinations are there? Well, there are 8 total vertices in the cube. So it's going to be 8. Okay, so this is number of vertex destinations times, okay, and then that edge has to stay attached to the vertex. It can't like detach itself and go somewhere else, okay? And so that edge, all that edge can do is go to one of 3 positions around that. There are 3 edges attached to that vertex, wherever it happens to go, right? Right, so these are edge destinations, right? So 8 times 3 is equal to 24, which is exactly what we got. It's right there. See the 24 sitting right there? So once again, you know, there are at most 24 possible symmetries for the cube, and we found 24 the other day. And let's just briefly describe what those were, just so that we're completely comfortable with this. Okay, one of these things, it says the rotation facial axes. Okay, rotation facial axes. Okay, so what's up with that? Let's see. So that was these things like this. So you could put a axis right through the middle of opposite faces. Okay, right through the middle of opposite faces for this thing. Okay, and let's see what's going to happen if I do that. And by the way, there's a total of 6 faces, so there are 3 of those. Okay, there are 3 of those things. Okay, and how's this going to work? Well, you can kind of spin around like this. Okay, you can spin around like this, and you can see that like the top vertices up here kind of go in a little 4 cycle together, and so do the bottom vertices. Okay, so if I take any pair of faces, and there are 3 of those, I'm going to have 4 cycles, and there are going to be 2 of them. Okay, so so that's how we got those ones. Okay, and what else did we do? Well, we also had, so we had these rotation facial axes. Okay, there were 3 of those And we spun those around. Those were 4 cycles, and there are 2 4 cycles when we do that. Okay. What about like opposite edges? Okay. What about opposite edges like this? Well, if I do opposite edges, okay, then what's going to happen? Well, I'm going to spin things like this, right? I can spin these, I can put an axis through opposite edges like this, and I can spin these things. And it looks like every single pair of vertices, whether it be these two or what about these two down here? These two down here and these two up here are in a little 2 cycle together. And what's going on with what's going on with these vertices here? Well, down here, you think about it, these opposite edges. So if I spin on these things like that and like that, I'm back to the beginning. So like here I have opposite cornered vertices that are in a little 2 cycle together as I'm spinning this thing around. Okay. So it looks like I have x2 to the 4th for those ones. That's axes midpoint rotations here. I think that's what I called this one right here. Okay, axes midpoints of opposite edges going like this. Okay, I have 4 2 cycles, and there are 6 of them. Why? Because there are 12 total edges, and each pair of edges that are opposite each other gives rise to one of these. Okay, so that's why you have 6 x2 to the 4th. Okay, and what else? Let's see here. I have opposite vertices. Okay, that was this. Remember, we were kind of rotating in opposite vertices. By the way, there are going to be 4 of those. Okay. And what's going on with this? What's going on with this? Well, so think about this for a minute. If I put an axis through the middle, let me kind of expand this so you can see a little bit better here. If I put an axis through opposite vertices like this, what's happening? Well, there are going to be 3 vertices, these 3 right here. Okay, as I spin this, those are going to spin into one another. And then there's going to be 3 vertices down here also that are going to spin into one another. Okay, so I have 3 up here and 3 down here that are spinning into each other. Okay, so that means I have a couple of things that are just staying where they are, right? Those are just 1 cycles, the top and the bottom vertex. But the other vertices split into groups of size 3, and they just rotate into one another. Okay, so I have 2 3 cycles when I do that. Okay, and how many total of these do I actually have? Well, I have 4 of those, right? So I have 4 of those particular things. Okay, so I have 4 total things where I've just paired off opposite vertices. All right, so yeah, let's let's kind of put the pieces together here. Let's look at each one of these summands and just justify where they're coming from. So the rotation facial axes, so think about it. Again, these were the ones that came from pairing opposite edges, yes? Okay, and we have to think about how many symmetries I'm going to get here. Okay, so either I'm going to rotate by, like 90 degrees. Okay, and if I rotate by 90 degrees, then what? If I rotate by 90 degrees, then that's going to put the top vertices in a cycle of length 4 and the bottom vertices in a cycle of length 4. Yes? So I'm going to put the top vertices in the cycle of length 4 and the bottom vertices in a cycle of length 4. Okay? So, so that means I'm going to have x4 squared. Okay? And what is the deal? What's the deal with that? Well, so 90 degrees, rotation by 90 degrees. and rotation by 270 degrees are both going to be length 4 cycles on the top, and there's going to be 2 of them, okay? But the problem is 180 degree rotation, that actually puts things into cycles of length 2. If I rotate by 180 degrees like that, these 2 guys are rotating into each other, yes? Okay, these 2 guys are rotating into each other, and these 2 guys rotate into each other. And you're gonna have opposite cornered things on the top and bottom going into each other. So that's actually 4 2 cycles, which is where this thing right here is coming from, okay? So this 2 sitting right here comes from 90 degree rotation and 270 degree rotation, because those are gonna give us 2 4 cycles. And the other one, which is 180 degree rotation, is consists of 4 2 cycles, right, with opposite cornered things on the top and bottom. And where's the 3 coming from? Well, the 3 is just talking about how many different pairs of faces do I have. Does that make sense? Okay, so that's what that factor of 3 is coming from. So overall, for each pair of faces, right, and there are 3 pairs of faces, which is where the 3 comes from. For each pair of faces, I have 2, I have 2 situations, 90 degree and 270 degree, that give rise to 2 4 cycles. And I have 1 situation where it's 4 2 cycles, okay? Of course, x1 to the 8th, that's just the identity. Then going over here, axis of midpoints of opposite edges like this, okay? This one's sort of easy, right? This is the one where we're going like this, okay? There's a total of 12 edges, so there's 6 of these, and each one puts the vertices, all the vertices, into cycles of length 2, okay? All of them are. The top and bottom, or the top edge, those 2 are cycling back and forth. Same thing with the bottom. And then these opposite diagonal corners are kind of rotating into each other, yes? So that's why you have 4 2 cycles for these ones. So that's fairly straightforward to see. Okay. And then opposite vertices, that's this situation like this. Okay. Opposite vertices like this. Well, how is this working? Let's see. I have a total of 8 vertices. And so that means there are 4 pairs of those, right? 8 vertices, and there are 4 pairs of those. And we already talked about why it is that since there's 3 edges coming out here, I get these 3 vertices that are rotating into each other, yes? And same thing on the bottom. So I get 2 3 cycles, okay? So the 4 that's sitting right there is talking about the number of ways to pair those vertices together. What's the 2 coming from? Well, that's either 120 degree rotation or 240 degree rotation. And then we're back to the beginning, right? So overall, we have 1 plus 6 plus 3, that's 10, plus 6 is 16, plus 8 is 24 total symmetries on the cube, okay? And again, I am going to actually let you think about the octahedron on your own. That's kind of an interesting exercise. Okay, but that's just a further rundown of what was going on with the cube. Again, facial rotations, but you do have to think about 4 cycles versus 2 cycles. 180 degree rotation gives you a bunch of 2 cycles. You have the axis midpoint situation, right? That just creates a bunch of 2 cycles. And then you have the opposite vertices axis of rotation as well. Okay, so hopefully this little thing right here kind of helps us see that a little bit clearer. Okay, I'll let you think about the octahedron, but let me just say, can we actually, without even knowing anything at all, could you justify why this is a 24? Okay, what could we possibly justify why this thing is a 24? Yeah, well, I mean, think about it. The octahedron has a total of, okay, so what this looks like, it kind of looks like a tetrahedron. but there's 4 triangles going down instead of 3 from a point. There's 4 triangles coming down. And you basically have one stacked on top of another. It's like 2 pyramids put together. Okay, so that means you're going to have a total of 8. You're going to have a total of 8 triangles, because that's why it's called an octahedron. And you're going to have 6 total vertices. 6 total vertices. So you're going to have 4 edges coming off of each one of those vertices. So if you do the vertex edge thing again, how many destinations, right? So how many vertex destinations are there? Well, 8. And how many edge destinations? And how many edge destinations at each one of those vertices? Well, that's where it gets a little bit. That's where it gets a little bit interesting. Okay, there are 8, or sorry, not 8. Not 8. Excuse me. Okay, not 8. There are how many vertices? A top and a bottom, and there's 4 around the middle, so that's 6. Okay, and now how many edge destinations? Remember, we kind of fixate on one edge coming out of a vertex. Well, there's 4 possible destinations for that edge around its vertex. Okay, so 6 times 4. So this 6 right here is the vertex destinations. This is the vertex destinations, and this 4 right here is the edge destinations for an edge that we've kind of distinguished as being attached to that specific vertex. So that shows that there can't be any more symmetries than 24. And in fact, if you think about it, the octahedron, you can actually find 24 distinct symmetries. Okay, but I'll kind of let you think about that, because I want to talk a little bit about the octahedron, or not the icosahedron. Yeah. Let me clear this because it's starting to get a little bit messy here. Okay. Yeah. Okay, so let's move down here and talk about the icosahedron. Okay, and look at this, 60. Okay, 60. Apparently there are 60 symmetries. 60 symmetries. Well, once again, what we can do is we can say, well, how many vertices were there? Okay, well, there were 6 around the top and there were 6 around the bottom. So there's 12 total vertices, right? So if I fixate on one vertex, and by the way, there are 5 edges coming off of each one of the vertices. You see that? Those are the blue lines. You see that? Okay, so there are 5 edges coming off of each vertex. So if I fixate on one vertex and one edge, okay, how many destinations are there for a vertex? Well, there are 12 destinations. And how many edge destinations are there? Well, 5, because I just have to pick one of the 5 edges around that fixated vertex. So this 12 right here is vertex destinations. And 5 is the total number of edge destinations about that fixed vertex, right? So we know that there can't be any more than 60 symmetries, because there are only 12 places I can send a vertex and only 5 possible destinations for an edge attached to that vertex. 5 times 12 is 60. Okay, and indeed that's it. We're going to find out that that's precisely the number of symmetries here. Okay, so let's look at the icosahedron a little bit more closely here to see where all of these 60 symmetries come from. Okay, let's start with something that makes sense. So first of all, we can go to opposite vertices. Okay, and by the way, x1 to the 12th, identity, right? We know that at this point. So if I go to opposite vertices of the icosahedron, okay, so opposite vertices of the icosahedron, okay, so there's like a north and a south pole, okay? And by the way, how many pairs of those are there? How many pairs of opposite vertices are there? Well, there's 12 total vertices. This thing is as symmetric as you can imagine. 12 divided by 2 is 6. That's where this 6 is coming from right here. See the 6 sitting here? Okay, so there are 6 right? So that 6 is going to be contributed. And now we have to think about, okay, how do I rotate? Well, okay, 108 degrees, 108 degrees, 108 degrees. You know, actually, no, it's not 108 degrees. How many degrees is this? I have to go, I have to divide this thing by 5. Okay, what's 360 divided by 5? Not 108 degrees. 360 divided by 5 is 72 degrees, not 108 degrees. I was doing the complement. Sorry. So 72 degrees, 72 degrees, 72 degrees, 72 degrees. Okay. There are 4 rotations before I get back to the beginning. Okay. And any one of those rotations is going to induce a cycle of length 5 among these vertices up here and among these vertices down here. Okay. So like if I'm spinning around this north and south pole, whether I'm doing 72 degrees or I'm doing 144 degrees, all of those are going to induce a cycle of length 5. And the main reason is because 5 is prime. Okay. I'm not going to like end this early the way I did with the cube. In the case of the cube, I was able to write 4 as 2 times 2, right? And so when I did 180 degrees, I got 2 cycles upstairs. But that's not going to happen here because 5 is prime. Okay. So whether I rotate by 72 degrees or I rotate by 144 degrees, or I rotate by 200 and so what's the next one? 144, 216 degrees. All of those are going to induce a cycle of length 5 among the vertices upstairs and the vertices downstairs. Okay, so that's why you have 4 of these rotations that induce two 1 cycles, namely the north and south pole, and 2 5 cycles. And again, the 6 is coming from the total number of ways to pair up, the whole number of ways to form a north and a south pole. Okay, so that accounts for this summand right here. What about this summand? Opposite edges. Opposite edges, like this. Okay, so opposite edges. So I'm going to go, right, I have these opposite edges like this, and I'm going to spin like this. Okay, like this. Okay, so opposite edges, I'm going to spin like this. Okay, so that's an interesting little symmetry. Okay, so opposite edges, I'm going to put an axis through the midpoint of those, and I'm going to spin that thing around. Well, what do you think is going to happen? Well, I go once, I go twice, and I'm back to the beginning. So that means every vertex, no vertex is fixed, and every vertex is in a little cycle of length 2 with another vertex. So for instance, this vertex right here, I think that's labeled number 7, and this vertex on the back side, which is labeled number 3. Okay, as I'm spinning those, you see 7, 3, 7, 3, etc. And those things are spinning into each other like this. So you're gonna have 6 cycles of length 2 because there was a total of how many vertices? 12. Okay, so you have 6 cycles of length 2 for that particular thing. Now 15 pairs of opposite edges. That simply arises from the fact that if you go and you count all of the edges, okay, so let's try to count all of the edges for this thing. Okay, so for instance, upstairs at the North Pole, 1, 2, 3, 4, 5. And then if I go around the base of this, 1, 2, 3, 4, 5. So that's 10. Okay. And then if I do the same thing down here, there's going to be 10 around the South Pole, like encircling and kind of going down to the South Pole. And then I just have to count the belted edges around here. Okay. And how many of those are going to be? So I had 10 and 20. And let's see, how many edges do I have here? Well, I kind of zigzag. I'm going to start with this 1 right here. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10. Yeah, so I have 10 edges kind of going around this little belted thing. So once again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm back. So 10 edges kind of zigzagging around that belt. So 10 upstairs, 10 downstairs, and 10 zigzag edges going around. Okay, so there's 30 total edges. Therefore, there are 30 divided by 2, or 15 ways to pair those things off. Okay. So again, we have 15 of those symmetries, and each one kind of split up all the vertices into 6 cycles of length 2. Finally, what's going on with this? Okay, so opposite faces. Okay, so now I'm just, I'm going to a flat spot like this, right? So I have a flat north and south pole, those faces, and the faces correspond to triangles, correct? And we already said that there's a total of 20 of those. So there's 10 pairs of opposite faces. 20 divided by 2 is 10. That's where this 10 came from. 10 pairs of opposite faces. Okay? And what's up with these things if I start spinning them? Okay, so it looks like the north and the south pole, north and the south flat poles, it looks like are kind of creating cycles of length 3 among those vertices. Okay, cycles of length 3 among those vertices. But then kind of look at the vertices, going around the middle right here. They kind of form a little zigzag pattern, like this. Okay, and as I'm spinning those things around, okay, as I'm spinning those things around, there's a total of, so there's 3 upstairs, 3 downstairs, and let's see, so that means there's 12 of those, okay, 12 of those, and the kind of peak zigzag vertices, okay, so in this case, what are the peak zigzag vertices? I don't know if you can see them very clearly, but the peak zigzag vertices are 10, right? So 8, 10, and 3, okay? 8, 10, and 3 in this particular case. So 10 is right there. 8, 10, and 3. Those guys are in a cycle of length 3 with each other. And then so you have the peak zigzag guys, but then you have the trough zigzag guys. Those things are going to be in a little cycle of length 3 together as well. So the vertices around the top face, the vertices around the bottom face, those are in a little 3 cycle. And then you have the zigzag belt of vertices. There are 6 of those, but those split up nicely into the peaked vertices that are going to be in a cycle of length 3, and then the troughed vertices that are going to be in a cycle of length 3. So all told, you have 4 cycles of length 3, okay? 4 cycles of length 3. Okay, and there are 10 ways to pair off faces since there were 20 total. And where's this 2 coming from? Well, that's just, 120 degree rotation versus 240 degree rotation. Okay, so there are 2 separate rotations that I count for when I do that. Okay, so we have completely described all of the symmetries. We've come up with, let's count them now. 1, 4 times 6 is 24, it's 25. And then we have 15, which gives me 40, plus 20 is 60. We have them all. We have all the possible symmetries here. And this is the icosahedron's cycle index polynomial. Okay, that is fascinating. That's some beautiful mathematics there. Okay, so again, I want to challenge you to think about in your mind what's happening with the octahedron. Okay, you can kind of try to draw a picture of that. Maybe I'll actually do that right here. Let me shrink down my picture and I'll draw a little pic of the octahedron. Okay. So what does a pic of the octahedron actually look like? Well, it's going to look like this. Okay, so okay. Like this. Well, actually, no. That is horrible. Okay, let me clear that out. Let me actually go over to something else, and I'll share this. And this will be the last thing that we'll do for today. Yes. Okay, here we go. Let's go over here. Okay. Let's try to draw this thing. Okay, so the octahedron, what you basically want to do is you want to first kind of draw the middle part. Okay, and the middle part, the thing that goes through the middle is basically a square. Okay, so, and then you want to draw the top of this thing. Okay. Okay, there's part of it. And then the bottom. Okay. There's the octahedron. Okay, and I will let you think about what all of the possible symmetries of that thing is, but that is a beautiful figure for sure. I actually had one somewhere, but it turns out it's not like a perfect octahedron. It ends up, it unfortunately is not a perfect octahedron, but I'll let you think about the symmetries for that and why, you know, why there are 24 of them, which is, I think, what we had, I believe. Yes, there are 24 of them. I'll let you think about why there happens to be 24 of them, and then think about why the cycle index polynomial is what it is over there in the notes, okay? So be on the lookout for updates to the notes next week. I'm gonna try to give a much clearer presentation of Polya's enumeration formula. That will be the last topic of the semester, and then we will just enjoy the rest of our time together, working on problems, thinking things through. I'll probably give out the final a little bit earlier than I normally would, so that you can start, toiling away on that. Other than that, I pray that you have a good weekend. That this is a great time for you, that you can relax and just enjoy the fact that that your future hope resides in the person and work of Jesus Christ. It's an amazing truth to behold. All right, have a great weekend.